Alright, today we're going to talk about speed, and we're going to relate it to both physics and chemistry. So you can think of it as like a crossover. So when we think of speed, that's going to be your distance traveled divided by your time. For example, when we're driving a car, our speed limit is usually in miles per hour, so that's miles over time. In our meme, my girlfriend said she needs some time and some distance. Is she calculating the speed? So when we think of it as a graph, the speed is a slope when you have distance traveled on the y-axis and time on the x-axis. Because if slope is rise over run, then our slope of a distance time graph would be distance over time, aka speed. And if the slope is 0, like how we see here, that means that you're not moving. You're not changing your distance. Your distance is staying the same and time is progressing. So if your distance is, you're not changing distance and you're not moving. Over here, it says that our distance is decreasing from our starting point. So that means that we're getting closer to where we started from. So over here, the distance is increasing over time. And we're getting further away from where we started. And if the slope is going down, then you're getting closer. So then we think about this from the math perspective. Let's say it takes Serena 0.25 hours to drive to school. She has to go 16 kilometers, and we want to know what is her average speed as she drives. And then we'll convert that to meters per second, bringing back that conversion factor we learned a long time ago in chemistry. We'll start off with a formula. We know that speed is distance over time. We said that she has to go 16 kilometers. It's going to take her a quarter of an hour. We divide those two and we get 64 kilometers per hour. Kilometers over hours, distance over time. Now we got to convert those 64 kilometers into meters per second. We're in kilometers per hour and we want meters per second. So step 1, we'll set it up with kilometers per hour. And we want to get rid of that kilometers and change it into meters. And there's 1,000 meters per kilometer, and those kilometers cancel out because that's what things do diagonally. Now let's deal with the hours. So we'll put hours on top so that they cancel, and minutes on bottom. But we don't want minutes. At the end of the day, we want seconds. So we'll cancel out the minutes and put seconds on bottom exactly where we want it. So let me plug all of that in. And when we multiply and divide all of that out, our hours cancel, the minutes cancel, and we're left with meters and seconds on the bottom. So we get 17.78 meters per second. So now we want to know, if we're given a graph, what's happening. If the car is stopped, what does that look like? If we're going at a constant speed, and if we're going backwards. So if we're stopped, that means we're not moving, our distance isn't changing, that's when the slope is 0. If we're going a constant speed, we're getting increasingly further away from wherever we're starting over time, so it's going to be increasing. And as we talked about earlier, when the slope is decreasing, that usually indicates you going back to wherever you started. So let's talk about this graph. We have Albert, Bob, and Charlie. And we want to know who won the race. So if we want to know who went the same distance in the least amount of time. So if they all went 100 meters, but A finished in the least amount of time. Albert finished in 10 seconds, Bob finished in 14, and Charlie in 18. So Albert was the fastest. Now I want to know who stopped for a break. If we look, this line right here shows no movement, so letter C, Charlie stopped for a break. And we went from about 7 seconds, we'll say, to 12, so he stopped for about 5 seconds. Now we want to know how long did it take Bob to finish the race. So B for Bob, we go to where he stopped running his final distance over time. He's finished in 14 seconds. Now if we want Albert's average speed, we're going to have to find the slope. So you're going to have, this will be your x1, y1, and over here will be our x2, y2. Remember, we talked about that here. y2, y1, x2, x1. So we said that our 1s are 0, we're just going to put 100 over 12. And so whatever that is, when you divide it, simplify it down, that's Albert's average speed. The distance divided by the time. And since this is the starting, we would have, I can pull it up, I think I can show it to you here. If we have y2 minus y1 divided by x2 minus x1, and we set that up so that our 2's are 100 and 12. So 100 are y, 0 is the 1, divided by 12 minus 0. y2, y1, x2, x1. So at the end of the day, we'll get 100 divided by 12, and you can plug that into a calculator to tell you what it is. So now let's think about this in terms of chemistry. We have these two lines. One goes 15 yards in 4 seconds, and the other one goes 30 yards in 4 seconds. So we want to know which one would represent particles moving at a faster speed. We usually assume faster to mean covering more distance over time. So the dotted line would be our faster particle because we went 30 yards instead of 15 in the same amount of time. How can we make particles move faster? Usually we can increase the temperature of our substance to make those particles have more energy. They absorb all that energy and they start moving around faster. And so if we want to know which line would best depict the gas phase and the liquid phase of moving particles, gas phase particles move faster than liquid phase particles. So the dotted line would be our gas phase, and the solid line would be our liquid phase. And that's it.